Okay, students, my name is Theodorus Gizau and I'm your physics teacher. Today we'll see about grade 10 physics, unit 4, that is magnetic field and forces. First, let us see about magnetism. What I mean by magnets? Magnets are metal materials. They are metal and they have an ability to attract what? Attract metals or metalloids. When we say metalloids, having a metal property and it's attracted by metals, and always magnets have two poles, north and south pole, and the field lines or the magnetic field lines always out from north and into south. But in electric field, the field lines are out from positive into negative. Here, but we have north and south pole, therefore they are outing from south and they are out from north and into north. This is the north pole, therefore they are out from north and into what? Southern pole. And there is a force between these two poles. If the poles are opposite poles, that means north south, there is an attractive force. But if the poles are like poles, north north or south south, there is what? A repulsive force. And the other thing is, as you see, for repulsive force, south south, north north is repulsive, but if it is north and south, there is what? An attractive force. And the other thing is, if we cut a single magnet into two magnets, we don't get a single pole. That means if you cut this magnet, the north poles and the south pole is not separated, and the cut or this part is this one, and it creates what? A north pole at this point. And this one also produces what? A south pole at this point. This indicates that we don't get or we don't have a single pole, either north or south pole separately. The other thing is magnetic domain. Magnetic domain is a region where magnetic force is uniformly magnetized. Magnetic domain is a region where uniformly magnetized. When we say uniformly magnetized, each north pole of a magnet is connected to another south pole of a magnet. If you see this, north and south is connected. Here also north and south is connected, and north and south is connected. Here also north south, and north south. Therefore, we don't have any extra north or south pole. All north and south pole are connected. Such orientation is called uniform magnetization, and this uniform magnetization area or region is magnetic domain. But here, if you see this, north and south, north south is connected, but at this point there is an extra accumulation of south, and here also an extra accumulation of what? North. Therefore, this one is not uniformly magnetized. Therefore, this is not a magnetic domain. Okay, the other thing is magnetic field lines. How we can draw a magnetic field lines? When we draw a magnetic field lines separately, first, a single magnet can possess a magnetic field because it has north and south pole, and always the field lines are out from north and into south, and the field lines looks like this one. If you invert also south and north, it's always similar. But if you put north, that means like poles, there is a repulsive force. This repulsive force makes they could not touch each other. The two field lines, the field lines of this north and this north is not touch each other. That means they have what? A free space. But if it is unlike poles, north and south, the field lines are connected and out from north and into what? The southern. Therefore, this is the structure or the diagram for magnetic field lines. Okay, magnetic lines of force around a paramagnet. We have seen that. We have seen already the diagram. What is magnetic shielding? Magnetic shielding is when we shield when magnetic shielding is stopping or protecting a material being affected by a magnet. To do this, magnetic shielding comes in various forms depending on the equipment that is need to be protected, and therefore magnetic shielding means that protecting or stopping equipment from being affected by a magnet. And magnetic shielding limiting the penetration of what? The magnetic field using the barrier of conductive material. The other thing is charge in magnetic field or the right hand rule. Okay, magnetic field is a region where the magnetic force is what? Experienced. And to calculate the magnetic field strength at a point due to a current carrying wire is calculated by using what? Force, which is equivalent to the product of magnetic field strength times current times what? Length. And the current is that is passing through the wire, and L is the length of the wire. For example, calculate the magnetic field strength when the current of 4 ampere flows in the wire of 2 meter long, and if it produces what? 8 Newton force. As we said, F is equal to what? B I times what? L. If we are asked B is equivalent to force divided by what? Current times length L. Therefore, the force is how much? The force of the wire is, which is the created, is 8, and the current is 4, and the wire length is 2. Therefore, finally we get how much? 1 Tesla. Therefore, the SI unit of magnetic field strength is Tesla, and it is symbolized by T. Tesla. It is symbolized by T. The other thing is the definition of magnetic field. As I said, magnetic field is a region where a magnetic force is experienced, and to define the magnetic field at a point, consider a particle Q and moving at a velocity. Experimentally, we have the following observations. The magnitude of the force exerted on the charge is proportional to both V and Q, and the magnitude of the magnitude and the direction of the force depends on what? Both the velocity and the magnetic field strength. And the third one, or the third point, is the force vanishes when V is parallel to what? B, and the force becomes maximum where B is perpendicular to what? V, perpendicular to B. When the sign of the charge of the particle is switched from positive to negative or vice versa, the direction of the magnetic force also what? Reverses. These are the basic rules. Therefore, FB is equal to QV cross with B, and this cross product is cancelled, and finally QVB times what? Sine of theta, where theta is the angle between the speed and the field strength. This one is the equation which we use to calculate the magnetic field strength by a single charge. The magnetic force which is created by a single charge. As you see, QF is equivalent to QVB sine theta, and this one becomes 0. F becomes 0, where theta is equal to what? 0 degree, because sine 0 is 0. That means the velocity and the magnetic field are parallel, and F is equivalent to QV times B, where theta is equal to what? 90 degree. That means maximum. It becomes maximum when theta is equal to 90 degree. Let us see the 4 diagrams expressed here. These 4 diagrams shows us two different basic points. This one is left to right. This diagram indicates the field line is moving left to right, and this one shows from right to left. And if it is dots, it's out of the page. The field is out of, or the current is out of the page, and this one indicates what? Into the page. You must remember this. And when we illustrate some diagrams, for example, the field B is from left to right, and we have 2 charges, one positive and one negative charge, and at this point, what will happen? What will happen to the charges? And if it is moving in opposite direction, what will happen? What will happen? Positive or negative charge traveling either with or against the magnetic field passes what? Straight through the experienced net force. Therefore, either positive or negative, both moves what? In straight, and they are out straight forward through the magnetic field, as you see. However, now consider a charged particle moving with left to right or right to left through a normal to the magnetic field. That means by making 90 degree. If it is positive charge, and it is what? Dot is in or out, into or out. Therefore, as you see before, since it is dot, it's what? Out of the page, and the current or the field is out of the page, and the charge is moving through that perpendicular to the field. Therefore, at this time it bends such a like. That means moves what? Down. But if it is into the page, it moves what? Up. It moves up. Therefore, you must remember this, the movement of the charge. The other thing is, for the charge on the left, your thumb will point upward and indicates the way they curl. That means the thrust. And the movement is circular. Since it is circular, the circular path is involved by the centripetal force. Okay, let us do one example. As you see, we have two examples here, two diagrams. The first one is a positive charge is moving straight through the field, and this one is at an angle of how much? 60 degree. Therefore, let us do for A first. The charge is positive charge, and it's what? Proton, and the speed is also given. But here, since the angle here produced is 90 degree, we can use sine 90 degree, QVB times sine 90, and we get how much? 2.16 times 10 to the power of -40 Newton of force is exerted. And at an angle of 60 degree, we can substitute in the place of sine theta, sine 60, and sine 60 is 0.86, and finally you get this much value. Therefore, you must use the angle which is given between the speed and the field strength. This one is the direction of the magnetic field, and this one is the speed, the direction of the velocity. Therefore, you must take the angle between them, since theta is the angle between the velocity and the magnetic field strength. Okay, the other thing is additional comments in magnetic field strength. This one is an advanced part. Therefore, you must read this by yourself. Now, this one is repetition as well, but current carrying wire and magnetic field. As we said, there is a flow of current in a current carrying wire. We have seen how we can calculate the field strength in a current carrying wire. Now let us see how we can determine the direction of the current. As you see, if the current is moving up, if this one is the direction of the current, our thumb must shows to the direction of the current, and the way our four fingers curl is the direction of what? The magnetic field. Therefore, the current is up. This one is the direction of the magnetic field. If the current is moving down, our thumb shows to the direction of the current, and the way our fingers are curling is the direction of what? The magnetic field. Therefore, by using this technique, by using right hand rule, we can determine the direction of the magnetic field. The other thing is solenoid. In solenoid is what? A coil of wire, a wrapped wire. For this wrapped wire, we can calculate the magnetic field strength, and the strength of the field is dependent on for three basic points. The first one is the number of turns per meter, that is small n. Small n is number of turns per meter, and the permeability of free space, and the current that's flowing through the wire. And combining these all, the field strength is equivalent to the product of these three. The permeability of free space, the number of turns per unit length, times what? The current. Therefore, finally, you can use this equation to calculate the field strength in a solenoid, but small n is the number of turns per meter. You must remember that. Okay, we have one example here. Solenoid has 1000 turns per meter and has a current of how much? 2 ampere passing through it. Work out the field strength as at its center. This equation is true for the center of the solenoid, and the field strength of solenoid is maximum, or the largest field is calculated at the center of the solenoid. When you go away from the center of the solenoid, the field strength decreases. Therefore, always when you calculate by using this equation, you are calculating the field strength at the center of the solenoid. Therefore, we have 2 ampere of current, and this one is number of turns per meter, and the permeability of free space is also given. Therefore, the permeability of free space and number of turns per meter multiplied by current, and finally you got the field strength in the solenoid. The other thing is magnetic field and centripetal force. These two have a relation, because when a charged particle is moving in a magnetic field, it moves in a path called circular, and to move this circular path there is a centripetal force which keeps, or which makes the object in a circular path. Therefore, Fc is equivalent to Fb, and Fc is mv square over r, and Fb is what? Qb v. bqv, and v is cancelled by this v, and finally you got what? mv over r is equal to b times q. Here we have 5 variables. By rearranging, you can get different 5 equations. Therefore, by using this, you can determine the value which is you are asked. For example, here we have a mass, a velocity, and a charge. This one is mass, and this one is velocity, this one is charge q, and moves in a radius of this much, and you are asked to determine what? B. B is how much? From this, to calculate B, B is equal to what? mv over q times what? R. And m is how much? 1.7 times 10 to the power of minus 27 multiplied by v. V is 8.8 times 10 to the power of 6 divided by q times r. Q is how much? Q is 1 multiplied by 200. Therefore, by multiplying, and finally you can get the final answer. Therefore, you must apply this equation depending on the question you are asked. Okay. The other thing is the factor that determines the force on a current carrying wire. As we say, the force is calculated by using FBI times L times sine theta, where theta is the angle between the lengths and the field lines, or the current in the field line. Therefore, always the value of this magnetic force is dependent on the magnetic field, the current, and the length of the wire. Therefore, since it's dependent on these three, if the angle between the field and the current or the length is vary, the value of the force is also vary, because the angle theta is varying. Therefore, it is dependent on the magnetic field strength, the current, and the length. The magnetic force between two parallel current carrying wire. This is basic, but in this grade level, you only see this magnetic field strength relationship, and you learn on grade 12, you learn how we can calculate the field strength. But for now, between two current carrying wires, there is a magnetic force. If the current is flowing in the same direction, there is an attraction force, and if the current is moving in opposites, one is up and the other is down, there is what? A repulsive force. Therefore, if the flow of the current is similar, or if the current is flowing in the same direction, they attract each other, and if the current is flowing in opposite direction, they repel each other. Biot-Savart's law explains and drives this one. And for any magnetic field around a long straight wire is calculated by using this equation. You learn this on grade 12, and mu naught is permeability of free space, I is the current that is flowing through the wire, R is the radius. Since, as we said, the field is circular around the wire, the radius indicates, for example, if this one is a current carrying wire, the field is around this, and therefore at this point, if you are asked, this one is the radius. This one is the radius. Okay. For example, what is the value of the magnetic field at a point 3.5 centimeter from a wire carrying an electric current of how much? This much. The permeability of free space is this much, and the current is this much, and this 3.5 centimeter is must be converted to meter. Therefore, it becomes such a value, and finally, you can get this value. This value. Okay. These are some diagrams. You must see this by yourself and calculate the values. Here also another example. We did the same equation. The same thing is true for the previous example. You can use the permeability of free space and the current and the radius, and therefore you can calculate the value. And the other thing is current carrying wire in a magnetic field. If it is moving in the same direction and parallel, we have seen also this. If the current is in the same direction, for this there is what? An attractive force, because at the region between them there is an opposite. Therefore the wire is what? Attracts, and the wires what? Repels if the current is flowing in opposite direction. And to calculate the force between these two, either the attractive or the repulsive force, we use this equation. Here mu naught is the permeability of free space, and I1 is the current that's flowing through the first wire, I2 is the current that's flowing through the second wire, L is the length of the wire. The length of the two wire is equivalent, therefore you can take one of the two lengths, and R is the separation distance between them, is the radius R. For example, two long parallel wires carry a current of carry wire and separated by this much, as shown. This one the separation distance. Following illustration, wire current in this much, and the magnetic field is wire B has a current of this much, and the length is this much. From this up to this is 0.5. Therefore, if you are asked to calculate the magnetic field strength, as I said, we use what? Mu naught I1 I2 L over 2 pi, and L is also given, and this one is the radius is 0.1 meter. Therefore, finally you can get this much value. As you see, either the force is attractive or repulsive. You can determine depending on what? If they are parallel and anti-parallel. When we say parallel, the current is flowing through them is in the same direction, and if they are anti-parallel, the further current that's flowing through them is in opposite direction. Therefore, the magnitude is similar, but if they are flowing in the same direction, there is an attraction force. If they are flowing in opposite direction, there is what? A repulsive force. The other thing is electromagnetic induction. When we say induction, the production of currents by induced EMF, and this induction, these are galvanometer, and see this by yourself. Let us see the induction laws. The laws of induction. The first one is Faraday's law. Faraday determines or explains about the magnitude of the induced EMF, and he said that the induced EMF is proportional with, or he expressed that the induced EMF is equivalent to n is number of turns times what? Derivative or change in flux over what? Change in time. You must change d to change delta. You learn this on grade 12 about derivative or mathematics, but for a time being you must change this d to delta. Delta is change, therefore change in flux over change in time. And the direction of the induced EMF is determined by lengths. He said that the induced EMF is flowing in opposite direction to what? The input EMF. Therefore he makes what? He adds a minus sign. This minus sign is added by lengths. Therefore, the length current produced moving through a magnetic field is in opposite to the applied force. Because of this, we add a negative sign, and the combined equation is this one. The combined equation is this one. This one is the combined equation of Lenz's and Faraday's. Lenz's and Faraday's. Therefore, we can calculate by using this. And flux, what is flux? Let us see flux. Flux is magnetic field density or magnetic field strength density. That means magnetic field times what? Area A. Area A. From this, if you calculate the magnetic field is equivalent to what? Flux over area. Therefore, magnetic field strength is sometimes named as flux density. Flux density. Therefore, this equation is another equation which we use to determine the magnetic field strength in terms of magnetic flux and area. Okay, the other thing is the self-inductance and mutual inductance. Self-inductance and mutual inductance. First, when we say self-inductance, the induction because of its own induction. That means to calculate the induced EMF, this equation is used to determine the self-inductance. Self-inductance is symbolized by L. Self-inductance is symbolized by L, and from this induced EMF is equal to minus L di over what? dt. And rearranging this, you can get the value of L or self-inductance. Self-inductance is the induction which is produced by the coil by itself. The second one is mutual inductance. Mutual inductance is the inductance which is produced by the neighboring what? Coil. By the neighboring coil. Therefore, for mutual inductance, induced EMF is equivalent to minus of what? Let us neglect the minus. The minus indicate the direction. Therefore, mutual inductance times change in I2. Which one? The neighboring current, because which is created by the induced EMF is produced by the neighboring current divided by change in T. The only difference is the current. For self-inductance, the induction is created by the current or the coil which is by itself. Therefore, we use the current of the induction or the coil, and mutual is because of the neighboring. Therefore, we use what? The current that is flowing through the neighboring wire. This is all about induction. We have one example here. A current of 3 ampere is supplied to a coil of wire having 500 turns. But before that, these equations are some advanced, and you have learned on, or you learn on grade 12. That is about integration and derivation. But if you see, it's good for you. But if you don't know about these equations, don't mind, because you will not learn on grade 10. You learn only on grade 12. Therefore, you will see when you reach grade 12. Okay, let us see the example. A current of 3 ampere is supplied to a coil of wire having 500 turns and is given. And if the flux of this much is given, that means flux is measured in what? Webers. And through the center of the coil develops this in this second. Determine the average EMF induced in the coil and the coil self-inductance and the energy stored in the coil. First, let us find the induced EMF. To find the induced EMF, we use what? Change in flux over change in time, and the flux is given 10 to the power of minus 3, and the time is also 0.1 second, and the number of turns is 500 turns. Therefore, finally you get how much? 5 volt. And to get the inductance, the self-inductance, L is equivalent to, from this equation, L is equivalent to induced EMF times dt divided by what? Di, or change in T over change in I. Induced EMF is how much? Induced EMF is here? No, this is not right. From this equation, if you rearrange, multiplying both, no, the equation is, this is not right, this is not true. The equation which you derive from this is inductance is equivalent to induced EMF divided by what? Change in I multiplied by this change in T. change in T. Therefore, the induced EMF is 5 multiplied by change in T is 0.1. The current is how much? The current is 3. Therefore, finally, you can get by multiplying this 0.5 divided by 3, it's around 0 point something is the value. And the inductance is measured in Henry. Inductance is measured in Henry, and it is symbolized by H. The SI unit of inductance is Henry, and it's symbolized by capital letter H. Using the equation for energy stored in a coil, that is 1/2 inductance times current square. The inductance is, which we got here, is not right. The real value is 0.5/3, and you can substitute that and multiply by the current square. Finally, you get your answer. And the negative sign indicate that the stored energy from the work done on the circuit. Okay, these are the laws: Ampere's law, Faraday's law, Gauss' law. We have seen this. Therefore, this is all about electromagnetism or magnetic field and forces. This is all about that. Until next time, have a nice time.